this is n equals 1 is a special case. N is neither a prime nor a composite. Therefore, we need to deal this specifically when we are dealing with primes. N equals 1. 1 is not a prime, neither a prime nor a composite. So then when we have done with one, we will come to the main part of the function. So what we are doing is we start from 2 and iterate up to square root n plus 1. And we check whether this I divides n. If I divides n, okay, from the beginning I am maintaining a flag. This flag is true if the number is prime. The flag is false if the number is not a prime. So if there is any number which divides n in the range of 2 and square root n, it means that this number is not a prime. Then I set this flag to false, and then I break the function, break the loop, because I can actually return a false here, but to make it clear, I have written it like this. I am going to break the function because what I'm doing is I'm checking for a prime. If it has one factor, it's no need to check the other values, because if it has at least one factor within this range, it's going to be a composite. Therefore, I will set the value of the flag to false and return it. So this will give us whether a given number is a prime or not. Okay. So yeah, that's it. Okay, that is how we check for primes efficiently, because we are not going to iterate from the from 2 to n. We are going to iterate from 2 to square root n. So that will give us a huge advantage, because if we have n like this, let's say 10 to the power 10, this approach is going to work. But if we iterate from 1 to n, it will give time limit exceeded errors, right? So this is very efficient approach. Then we can talk about prime factors. I hope you know about prime factors, but I will say what prime factors are. Now, we can express any number using its prime factors. Prime factors. These are basic stuff. We will come into some deeper stuff lately. So prime factors. So let's say 24. We can express this as a multiplication of the powers of prime numbers. As a multiplication of the powers of prime numbers. For this one, we can say it like this. Now 2 is a prime. 2 is raised to the power 3. And it gets multiplied by 3. So it will give 24. So this is the prime factorization of 3. Okay. So in programming, in competitions, but we can't actually store it like this. So what we are doing is we maintain an array and we store 2 for 3 times. It means that the power of 2 is 3. And we store 3 like this. So the number of occurrences of a certain factor in this array is equal to the power here. That's it. So how we can construct this array? How we can construct this? That is what we are going to see next. So another algorithm. So what we are doing is we take 24 and we take the first prime number. Actually, we iterate from 2 to some unknown value. I will let you know the break-in condition shortly. But for now, we should start from 2. Now 2 is a prime. So we check whether this can be divided by 2. Okay, this can be divided by 2. This will give us 12. Then we check again that whether this is going to, is it possible to divide by 2? Again for this one. Yeah, it is possible. Then it will give us a 6. Then we check again. We can, divide it by 2 again. We will have 3. Now we check whether this can be divided by 2. Okay, we can't. Therefore, we will go to the next prime number. So the next prime number is now primes to the next number actually. Now say we have checked all this and we checked 2, we checked 3, and we have come to 4. And since we are dividing this number by the primes we are considering, at this point, this number will not be divisible by 4, for sure, because we have considered 2. 4 can be expressed as 2 times 2. If something can be divided by 4, it means that it can be divided by 2 for 2 times. Here, we have the same case. 24 can be divided by 2 for 3 times. It means 8 is a factor. But if we iterate this up to 8, when we come to this point, we will have a number which is not divisible by 8. Therefore, we don't need to actually consider only the, let's say, only the primes here. We can actually iterate from 2 to a certain point. So we will initialize an empty array first, and we will add these elements, these devices to this array. So now we have to add 2 for 3 times, 2, 2, and 2. Then 3 is not divisible by 2. Then we need to go to the next number. The next number is 3. This is divisible by 3. It will give us a 1. When we have this one, we need to break this. So we can have a while loop. Now, for loop is a iterator based loop, but while is a condition based loop. Now this is a condition. Once n is equal to 1, we need to break the loop. Therefore, the best choice is using a while loop. Now we had to append 3 here. Now we have this array. Okay. I have this function as well. I will show it with my Discord. Prime factors. What I'm doing is I'm initializing an array called f for factors. Then I start from 2. I'm not starting from 1 because 1 is not a prime. 1 is a special case. We need to actually get rid of one of these cases, because if you start from 1, this will be an infinite loop, because let's say n, and we are trying to divide it by 1. We have the same number. Again, we will try to divide it by 1. Then this would be an infinite loop. To make sure that we don't fall into that condition, we will start from 2. Then we check that this one, if n divides x, if x divides n, then we append x to the array, then we integer divide n by x and assign it back to n. Then we increase x by 1 and do the same thing. So that is how we implement this one. So let's run this one, and it will ask for an let's say 7. So 7 is a prime number, so it's a prime factorization would be 7. Let's say 24, and it will give the array. So this is how this works. You can find this algorithm in my repository. Okay, now that is how we check for prime factors. Then, so do you have any questions up to this point? If you have questions, you can drop it to the chat box. Then we are going to do an interesting thing. So what we are going to do is find the number of factors. Number of factors. Find the number of factors. So how we can do this? Now say we have the prime factorization of 24 as an array. Okay. So if we need to find all the factors of 24, what we can do? We can actually take all distinct subsets of this set, including the null set, and we can take the multiplication of the elements. For an example, let's take 2 and 2. This is a subset. So the multiplication of the element is going to be 4. So 4 is a factor. Then let's say we have taken 2, 2, and 3 out. So if you multiply all the elements, we will have 12. Right? So 12 is a factor. Then we can take the entire set up. Then it will give 24. If we take null set, it will give us 1. Okay. So if we take 3 2s, it will give us 8. But now here you can see that since we have 3 2s here, finding now we can have we can choose actually these 3 2s, in bunch of different ways. Let's say if we check for permutations here, we will have 6 permutations of 2 and 2. So we need to be careful about that. So what I need to emphasize here is, if we need to find all the factors of 24, what we need to do is we should find all the distinct subsets of this set and multiply the elements. Then it will give us factors of 24. So now what we need to do is we need to find the number of factors. So to do that, I will go back to this definition, 2 to the power 3 times 3. So now we have agreed that if we take a subset from this original set and multiply the elements, it will give us a factor. Now, what is the analogous expression statement for this one? We can, for a factor, we can take these 2 primes and we can raise this to any value. But we should be careful. We need to keep this number less than or equal to 3. Why? We don't have 4 fours. We have only 4 twos. We only have 3 twos. So we can use any number of twos, but that number should be less than or equal to 3. For this one, 3 has 2 possibilities. We can either use 3 or not use 3. So this should be less than or equal to 1. So we need to find, we can fill with numbers. Let's say we can fill with like something like this, to the power 1. So this will give us 12. We can fill it like this. This will give us 2. Or we can fill it like this. This will give us 1. So like that we can fill this with numbers. Now, see this square here. There are 4 possibilities, 4 possible numbers I can use to fill this box. 4 possible numbers, because we can use 0 as well. 0, 1, 2, and 3. We have 4 different numbers. For this one, how many? There are 2 different numbers. This can be filled. There is 4 possibilities. For this one, there is 2 possibilities. So we can find the number of factors by considering this combinatory condition, by using this information. So the number of factors is going to be 4 times 2, because we can use 2 for 4 in 4 possible ways, and we can use 3 in 2 possible ways. It is similar to something like this. We have 3 towns, let's say A, B, and C. To go from A to B, let's say we have 4 paths like this. And to go from B to C, we have 2 paths like that. So how many possible paths are there to go from A to C? We can take 1 path from here and 1 path from here. This path from here and this path from here. For every path in this, for every path to go from A to B, we have 2 different paths to go from B to C. So the number of distinct paths would be 4 times 2. So this is same. We have 4 possibilities here, 2 possibilities here, and all the number of total possibilities is 4 times 2, which is 8. So we have 8 factors for 24, and we know that. You can check it, right? Wait, see, here we have 4 factors. So now we need to write this for a general case. So that is how I approach a problem when I actually can't see the problem of the algorithm properly. I always take a concrete example like this, and I try to solve the problem for that, and make sure that you don't take a special case. So what I do is I always take a prime, something like 17. 17 is my favorite number when it comes to concrete examples. So take a prime and try. Now for this case, you can't take a prime because prime is a special case here. Therefore, you need to take a number. So for general case, let's say we have a number like this. We can actually write the prime factorization like this. E, A, alpha, K. These P's are primes and alphas are the powers. So alphas are integers, p's are primes. Okay. So now, if we need to find all the factors of n, we can use p1 for 1 plus a1 different possible ways. P2, there are 1 plus a2 because we can go from 0 to alpha 2. So there are alpha 2 plus 1 possible ways. For this one, there are 1 plus alpha 3. Likewise, we have 1 plus alpha a here. So we need to multiply all of these possibilities to take the number of factors. Say number of factors is 1 plus alpha 1, 1 plus alpha 2, 1 plus alpha 3, and all the way up to 1 plus alpha k. Okay. Now we can actually incorporate the product notation here. We can start from 1 and go up to k. And I have used the 1 index here instead of 0 index because it can confuse you. Actually, it has nothing to do with the answer. So this is alpha I. So if we can actually take this product, so that's it. So we can find the number of factors. So did you understand this? Can you give me a feedback? Yes or no? Please be quick. I have 20 participants here today, so I need at least 5 responses. Okay, got it. Yes. Okay. 3. Can I have 2 more? If you can't understand, please don't say no. Don't say yes. Please raise any questions that you are having. Okay. Okay. Now, another interesting case is sum of factors. And if you feel like these things are pretty basic, these things are not actually, I should teach these things. If you feel like that, please drop me a private message. Then if I see bunch of private messages like that, I will skip some parts. Sum of factors. Sum of the factors. Okay. So now what we are going to do is we will find the sum of all the factors. Say for 24, we have 8 factors, and we are going to add all those factors and find what is the answer. So no, for number of factors, what we say is tau n. This is how we denote it. So this number of factors of 24, we denote it as tau 24. I forgot to give the notation. Now sum of the factors, we denote it as sigma of n. So sigma of 24, how we can find this? We can find all the factors and add them. So we can derive a formula. I will give you the formula and explain how it gives the sum of factors. We can start from here and pi squared all the way up to pi alpha I. So how is this going to work? Let's say we have only 3 prime factors. Okay. So it will look like this. Let's say plus p1 squared all the way up to the number of occurrences of p1. Let's say alpha 1. And we have p2 squared and all the way up to p2 alpha 2. And we have 1 plus p3 squared plus all the way up to p3 alpha 3, like that. Now see, if you multiply this product, first we have 3 ones. So this will give you a 1. Then if we take these 2 ones and multiply with this p3, this will give you p3. And can you see that? Please don't skip anything really interesting. Okay, thank you. There is a good feedback. I was not sure that these things are important to you. Now, I am actually I have increased my confidence. Okay, so if you have any feedback like that, please forward it to me. Okay, now this will give us a P3. Now let's say something like this. If we combine these three, this will give us 1 times P2 times P3, sorry, times P3 squared. So can you see that all the possible combinations, now we have talked about this, discussed about these combinations here. Okay, so can you see that all the factors are built with this product? Because we will have all the elements from this array multiplying from all the elements from this array and from all the elements from this array. We take all the elements, we take all the combinations and multiply them. So we have all the factors of n. So this, and we have the summation. So we have the summation of all the factors. Now, this is not enough because we can simplify this further using the theories of geometric series. So we have this here, and this is a geometric series. So we can write the sum, and now we can write the sum like this: what pi to the power alpha I plus 1 minus 1 divided by pi minus 1. Is this correct? Let's see. So the Sn will be a times Rn minus 1 divided by R minus 1, right? So what is R here? R is pi. Okay, and n is number of terms. There are alpha I plus 1 terms because we start from 1, and here we have from 1 to alpha I. So 1 to alpha I, there are alpha I terms, and with 1 we have alpha I plus 1 terms. So this is the formula for the sum of factors. So there are a bunch of problems that you can see in C's, CACs and all. So you can actually use this formula to find that, because you are iterating from 1 to k. Now say your number is 24, but this 24 has 8 factors. So instead of actually iterating from 1 to 24, you can iterate from 1 to 8. So this is a huge advantage. Imagine if you have a prime here. So it would be very easy. Right? So this is also a very efficient approach. Then since we are talking about primes, I will give you common algorithm to find primes. That is called the sieve of Eratosthenes. I don't know if I pronounce this correct. And if I don't know whether I'm spelling this correct, but I pronounce it as the sieve of Eratosthenes. Actually, the pronunciation does not matter if we know the algorithm. So what we are going to do is our target is to have an array. Okay. The ith index of this array can have two possible values, 0 or a 1. If the index in the ith position is 1, it means this is a composite number. This is not a prime. If the value in the ith index is 0, it means this is a prime. So if we can have something like this would be really useful when we are solving problems, because there are a bunch of problems associated with the prime numbers. So if we want to find whether a number is prime or not, we can actually do it by just taking by constant time using this array. So for the ith index, we have two values, 0 or 1. So what does that say? It says that whether the number is a prime or not. If the value in the index I is 0, the number is a prime. If it is 1, it is not a prime. So how we can achieve this? We can actually have a very simple approach. Target, let's say algorithm. So what we are doing is we actually initialize an array all from zeros, all the way up to the 8. So this corresponds to, for my case, this is 0. This is 1. This is 2. This is 3. This is 4. Let's say this is 100. Okay. So I will add some more. Okay. So this is 5. This is 6. This is 7. This is 8. And this is 9. So what we are doing is we start from 2. Okay. We start from 2. We start from 2. And we set the indices where the number of the index is, if the index is a multiple of 2, we set the value to 1. If the index is a multiple of 2, we set the value for that index to 1. So we can actually iterate from let's say 0 to n, actually 2 to n. Then when we come to 2, we make all the multiples of 2 to 1. That is pretty convenient, right? Because multiples of 2 cannot be primes. That's it, because 2 is a factor for all of those numbers. Therefore, those are not primes. Then when we are done with that, we come to 3. Now 3, then we check whether 3, now the current value of 3 is 1 or 0. It means what we are doing is we are finding all the primes from 2 to n and set all the multiples of that prime to 1. Now say when we are done with 2, 4, 6, 8, 10, 12 up to 100, the even numbers up to 100 will have a value of 1. So we are not checking them when we are doing the iteration. But 3, there will be a 0 because 3 is not a factor of 2. Okay, 3 is a prime. So we set 3, 6, 9, 12 and all of them to 1. Then we go to 4. Okay, now there is a 1 in the 4, then we skip that. Then we come to the 5th index. Okay, that is a 0 because 5 is not a multiple of 2, 3 or 4. So that exactly gives 5 is a prime. Yeah, 5 is a prime. Then we set 5, 10, 15, 20 and all 1. Then we come to 6. Now we have 1 in the 16th index because it is multiple of 2 and 3. Okay. So then we skip that. Then we come to 7. So we continue like that. Then at the end, we will have an array like this. So how we should use this array? Where we should use this? And there was an interesting problem I have actually. Let's say counting devices. This is this. Let's try to find that. Sum of devices. Device analysis. Let's see this one. So is this? No, I can't find that problem. But what that problem said was, we are given a number, and we will have a number of queries. We are given a number n. Let's say we are given a number n, and we have multiple queries. Let's say Q1, Q2, and Q3. In the same test case, we have multiple queries. And for each query, we will have a number m, which is less than n. What we need to do is to check whether M is a prime or not. We need to check whether M is a prime or not. No, we are not given int. Actually, we are given some queries. For each query, we have a number M. We are given an integer. We need to find whether it is a prime or not. So we can have up to, let's say, 10 to the power 12 queries. We don't know. Let's say 10 to the power 20. This is also possible. But for each query, this M is less than 10 to the power 6. This is given. M is less than 10 to the power 6. But the number of queries, let's say we have n number of queries here. So this n constraint was something like this. So how to deal with this? Now we can't actually run a single algorithm for each of the queries to find whether it is a prime or not. Now say we take the first query and check whether it is a prime. Then we go to the second query, check whether it is a prime. And we go on like that. We should have to have 10 to the power 20 iterations. They will not allow that because we have time limitations. Therefore, 10 to the power 20 is not actually manageable when it comes to iterations. So what we do is we know this constraint. Now, if you have participated the session that we did for IEEE with all of my teammates, we have mentioned that we need to actually consider these constraints when we are solving problems. So this is an example where we need to be handy with those constraints. Now see, we know that this number is going to be less than 10 to the power 6. So before we take all of these queries, we make the sieve for 10 to the power 6. We make this sieve. Now this is not very time consuming because sieve of Eratosthen's algorithm is, the time complexity is near to O log n. This is a linear time algorithm. Actually, it is n log of log n. This is the actual time complexity, but this is almost equal to big O n. So this is a linear function. So it is very easy to have this sieve before we take the queries. Then once we have a query, what we are doing is we check the sieve. That's it. So we are not going to make the sieve for all the queries, and we are not going to check primes from iterating up to 0 to Q1, 0 to each query. What we are doing is we are having the sieve before we are taking the queries, and then we check the index. That's it. So we can solve it. Since the constraint for M is bit released. Okay. So we can use the sieve like that. Now, this time coders, we had something called to find E-prims or something. So what an E-prim is, let's say for primes, we actually reverse this prime like this. We start from the back, the latter part, and come to the front. So it will give us very well. We actually reverse the digits. Then if this resulting number is also a prime, this pair is an E-prime. So we had to print all the E-primes from 1 to 100. So to do that, we have the sieve first, then we iterate through the sieve. If we have a 0, it means this is a prime, then we can check whether the reversed integer is a prime or not. We can check it using the sieve. Check that thing also. So if we have the sieve before we tackle the problem, we can actually find whether a given number is a prime or not in a very efficient manner. That is how we can use this sieve very efficiently. Okay. So have you understand this? Understood? Can you drop me a message? I'm constantly asking for these feedbacks because I need to check whether you are following me or not. Make sure that you're not sleeping. Okay, have a yes. So a few people are responding. You got it. Okay, I have the same bunch of guys here. Okay, at least they can understand. Okay. Now that's it. Then actually we can extend this save of irretor states. Now here we had what we did was when we encounter a prime, we set all the multiples to 1. Instead, we can set all the multiples to the prime. Now say we iterate from 2, we encounter 2, and we set the value for the multiple of 2's to 2, not 1. Then I come to 3, and I set 3 for the multiple of 3. Then this array will have the lowest prime factor for each number. Say we start from 2, and we make the 4th index 2, 6th index 2, 8th index 2, likewise. And we come to 3, and we make the 6th index 3, the 9th index 3, and we go like that. So it will give us an array. The ith index of the array will contain the lowest prime factor of I. So I have this code as well. So where is it? This is the save of irretor states. I initialize an array with zeros. Then I check if not save. I hope that you know this when you are checking conditions. If you say something like, let's say, while 1, this is taken as while true. And while 0 is while false. Let's say if something. If 1 is if true. If 0 is if not true. So what we are checking here is if not CUI. So CUI will have a 0 if the number is a prime. So we are checking whether the number is a prime. If the number is a prime, then we run the inner loop. What we do is we start from 2 times I, means 2 times the prime that we are considering, and we are iterating up to n plus 1 with the steps of I. This will iterate through all the integer multiples of the prime, and we set it to 1. In the extended version, we do the same thing, but here we set it to the value of the prime, set it to I instead of 1. Here you can see we set it to 1. Here you can see we set it to I. So this will result in, okay, let's try it. Let's say 100. No, let's say 10. Oops. Set it. Okay, then we need to give a number to find the smallest prime factor. Let's say 8. And we can see 8 smallest prime factor is 2. This is taken from the array. When we give this argument, it will actually build the array. Then, yeah, like that. So this is the extended version of the CO filter states. And now we actually don't have time. I'm not sure whether we have enough time to discuss combinatorics, but we will do these things solidly. Okay. So then we will move on to modular arithmetic. Modular arithmetic. We will. Okay, don't have any questions. Modular arithmetic. So modular is something where we deal with the remainders. Remainders are pretty important. You know that. You know the remainder theorem and all, right? So you know how important a remainder is. So modular arithmetic deals with remainders. Let's say we divide 35 by, let's say, 8. And we have a quotient of 4 and remainder of 3. So in the modular arithmetic, we deal with this 3. We denote it as when 35 divided by 8, the remainder is 3. We say 35 mod 8 is 3. This means when we divide 35 by 8, the answer is 3. In programming, we can find it like this in Python. This will give us 3. This is the modular operator. Okay. So let's say another one. Let's take another one. What is 19 mod 8? I need quick replies. What is 19 mod 8? Okay, again it's 3. Yeah, so 19 is, yeah, 19 is 16 plus 3. So 16 is the smallest, is the nearest small multiple of 8 for 19. So the remainder is 3. Now, I need to emphasize 2 factors here. One is, with this information, we can write 35 as 8 times an integer, let's say q, plus 3. If the remainder of 35 when it is divided by 8 is 3, we can actually write it like this, 8 times. Now, for this case, this 8 is 4. Q is 4. So, something like that. So, say we have something like this. A mod M equals B. So, you can write A as by this. With the same argument, we can say A as M times Q plus B. This is correct. Okay, yes or no? Is this correct? If A mod M equals B, is A equals to MQ plus B, where Q is an integer. Okay, yeah, this is correct. So you need to keep this thing in your mind. And the next thing that I need to emphasize here is, if we take these two, you can see that both of these numbers, when we take mod 8, it gave the same answer. It means 35 and 19 has the same remainder when it is divided by 8. So we say these two are a congruent pair with respect to modulo of 8. I will rephrase that. Since we have the same remainder when 15 and 19 both divided by 8, we say 35 and 19 a congruent pair with respect to modulo of 8. We denote it like this. 35 is congruent to 19, and we need to specify the module. So we read this as 35 is congruent to 19 mod 8. It means 35 and 19 have the same remainder when divided by 8. No big deal. Right? Understood? And there are some special properties of this modular arithmetic you need to consider. It means I will go to the next page. Let's say A plus B mod M is equal to A mod M plus B mod M. And we have the same thing for the subtraction. M equal to A mod M minus B mod M. And we have the same thing for multiplication as well. We have A mod M. You can actually prove these things. Try to prove them. I will not do the proof because I don't have enough time today. You can actually prove these things. So what I am saying is addition and subtraction is distributive under the modular operation. That is what I'm saying. So this congruency is another thing that you should consider. Now for an example, I will ask another question. What is the time now? Okay, I have about 40 minutes left, I guess. So we will try to cover most of the topics. So is this congruent equation correct? Let's say 21 is congruent to 38 mod 7. Is this correct? We need quick answers. Is this congruent equation correct? Congruent relation correct? Why? Yeah, this is not correct. Why? When 21 is divided by 7, the remainder is 0. But when 38 is divided by 7, the remainder is 3. What about this? This 24 is congruent to 38 mod 7. Yeah, correct. So this is correct. It is because uh, 24, when 24 is divided by 7, it will give 3. So does 38. And then let's say something like this. How about this? Um, is this correct? Can you do it by your head? You can't, right? Because no, actually you can do this. It's not a big deal, but there is an easy way to do this. What you are going to do is you are subtracting these two numbers and you find the difference between these two numbers and check whether the difference is divisible by 17. You subtract 11,953 from 11,990, you will get 34. 34 is divisible by 17. It means that this congruent relation is correct. So you can actually prove that too. Actually prove it. Prove that means if uh, let's say A is congruent to B mod dem, then you should prove that A minus B can be divided by A. That is what you need to show. Okay. So yeah. Then we have something called congruent classes. I will quickly skim through them. Congruent classes. So congruent classes means now for to describe this one, I will actually take m equals 7. It means I am trying to consider the modular with respect to 7. Mod 7. I'm going to take mod 7. So there will be some integers where it is divided by 7. The remainder is going to be 0. Say 0. And there might be some integers when it is divided by 7, remainder is 1. And we will have up to 6. We can't have remainder of 7, right? So there will be bunch of integers here. Now I will ask you a quick question. Uh, what will be this? The answer for this one. Can you give me the answer for this one? Minus 1 mod 7. What is the remainder when minus 1 divided by 7? Yeah, exactly. 6. Why? How to find the modulo? Let's say we need to find 25 mod 7. How to find this? You take the nearest small integer multiple of 7 to 25. What is the nearest integer multiple of 7 to 25? It is 21, right? Then you subtract 25, subtract 21 by 25. Then you will have 4. So the answer for this is 4. For this one, what is the nearest small integer multiple of 7? It is minus 7, right? It is minus 7. Then you need to subtract minus 7 from 1 and this will give you 6. This is 6. That is how you find the modulo for negative numbers. Now, this will have something like this, some integers like this, okay. And one will have like this, okay. Then two will have, and this continues from minus infinity to plus infinity. So we have and I will write another one, and you can complete this table after the session and like this. Now what I need to uh, point out here is now these are called congruence classes. Now 7 has 6 congruence classes, set of integers which satisfies this equation. Let's say A is congruent to B mod M. So depending on this B, we will have 6 congruence classes. When M is 7, we can have, for this one, we can have 6 values, because 7, if we take 7, we will have the same class again. Okay. So here we have congruence classes like this. So say I take one from this class and one from this class and add. If we add 2 plus 1, we will have a 3. And say if we add 5 and 6, we will have 11. And if we add, let's say 8 and 9, oh, this is incorrect and no one mentioned. This is 16. And this is 17. Okay. So if I add 8 and 9, it will give me 17. And you can see that if we take one congruence class, let's say this is R1 and R2. If we add R1 and R2, always we will have an element from R4. Oops. Is it R3? Sorry. From R3. This is true for any case. And we have the same thing for subtraction and multiplication. You can check that. Now, for an example, if we take 3 from this class and take 1 from this class, and we take the difference, we have 2, and we are in this class. Then we can do the same thing for 10 and 8, and we have 2 here. So that is how it happens. So these congruence relations are there for any operations, not for any operations, only for subtraction, addition, and multiplication. But for division, these things will not work. So there is a special way to deal division in modular arithmetic. I will get into that later, and it will give you huge advantages when you are dealing with problems. Okay, so next I will talk about Diophantine equations. And I will focus on linear Diophantine equations. So do you know what a Diophantine equation is? I hope some of you know and some of you don't know. It is an equation like this. Ax plus by equals c. A, B, C are integers and A, B, C are not. They are given. They are integers, not. What we need to do is we should find x and y. Now this is a very easy case. What we are doing is we can plot the graph for this one, and all of these points would be solutions for this equation. But here we have a different condition. The condition is x and y are also integers. So we need to find integer solutions for this equation. We are given an equation like this, and we need to find integer solutions. There might be a bunch of solutions, and there might be a bunch of solutions, so there might be no solutions. But the specialty here is we need to find integer solutions for x and y. So for an example, let's say 5x plus 2y equals 11. For this one, we can have a solution as 3y equals minus 2. So this would satisfy this equation. Let's say x is 3, 5 times 3 is 15, minus 4 is 11. But this is not the only answer. There might be some other answers, some other pairs, for example. Okay, so this is a linear definite equation, and what we are going to do is we are trying to solve it. How we are going to solve it is using Euclid's algorithm. This is an algorithm you use most of the times. Euclid's algorithm. Okay, Euclid's algorithm. Now, you know about, do you know about greatest common divisor and least common multiple? Do you know that? Can I have feedback, please? Quick, because it's almost 8:30 and we have not touched combinatorics yet. Okay, yes. GCD is, let's say we have two integers. GCD is, if we find the factors of these two guys, A and B, GCD is the largest common factor. Largest common factor. GCD is largest common factor. So, Euclidean algorithm, what Euclidean algorithm does is, it will solve this linear definite equation. Now, there is a recurrence relation where we can find GCD of A and B. I will not touch that. So, Euclid's algorithm will solve this linear definite equation. Actually, this is extended Euclidean. Euclid's algorithm is, we have a recurrence formula for this one. Euclid's algorithm is, okay, let's consider that one too. AB, we can, because this is interesting. How to understand this? The understanding of this is interesting. We have a recurrence relation like this. GCD of B and A mod B. Let's say this is correct or not. When B is not equal to 0. Now, can you understand how this is correct? This says that if the greatest common divisor of A and B divides A and B, that is a fact that we know. Greatest common divisor divides A and B. That's correct. And what this says is it divides B and A mod B. It divides A mod B as well. It divides A and B. That's correct. The factor should divide these two guys. But what it says is it divides A mod B as well. So how you can see that is, let's say this is A. Now we will say A is greater than B. So this is A. This has the length of A. Okay, I'll take something similar to that and say this length is similar to A and this small length is similar to B. And we have two B's here. And this part here is A mod B. You can see that, right? Because we have two B's and this is the remainder. That is A mod B. And say the greatest common divisor is X. If that is the greatest common divisor, it should divide both A and B. So it will be something like, let's say this. This length is X. It should divide B like this and A like this. And you can see it should be a factor of this one as well. Otherwise, this is not a factor of A, right? So it should be a factor of A mod B. That is what I have mentioned here. That is the Euclidean algorithm. You can actually code this recursion. You can find it on GitHub. So this is how we can solve using Euclid's algorithm. So by extended Euclidean, what we are doing is we actually encounter this and solve this mathematically first. Then we code it. We use the mathematics to actually solve this. Use this algorithm, right? So what we are doing is now what we are trying to find is two integers x and y which satisfies this equation. And we know that we can replace GCD AB by this one. Okay. So it will give problem like we can replace A by B and B by A mod B. B x dash plus B A mod B. Let's say we are trying to find some integers like this. Now this will work, right? This will work. And now we need to simplify this. To simplify this, we need to write this A mod B in a familiar form. So how we can do this is, now say we have, how to explain that? So here you can see that A mod B is this distance. How we can take this distance using B and A? That is, you can take A, this distance, and subtract this distance. So how to find this distance? This is 2 times B. This is 2 times B. Where does this 2 comes from? That is the integer division of, if we integer divide A by B, we will have to, it will always give us the flow value. Flow is denoted like this. This is, if we have a decimal, you only take the integer. You have something like this. If we take the flow value, you will have 2. So if we, this is 2. Now for this case, this is 2. If we multiply it by 2 and subtract by A, we will have A mod B. We have something like this. So if we plug this here, we will have an equation like AY dash plus B x dash minus B over A. Now this simplification does not matter. So you can actually find this algorithm in the GitHub, so you can use that in a competition. So now what we should do is, we can replace x by y dash and y by this guy. So if we use this one in a program, you can easily solve this using Euclid's extended Euclid's algorithm. And we can use this extended Euclid's algorithm to solve a linear Diophantine equation. Let's say we have something like this. Now, this is very easy. Even if you did not understand extended Euclidean, it's okay, because you can actually take the code for extended Euclidean using a generator, a generative AI or something. Then you can apply it here. So this is a linear Diophantine equation. Let's say we have something like this. And this is clear. Okay. So this has solutions if and only if this has solutions if and only if C is a multiple of GCD AB, like this. If this condition does not satisfy, this is not going to work, because this will not have answers. Therefore, this condition should be there. So instead of solving this for C, you can solve this equation. Now for this one, the GCD of AB is 3 and 12 is 3 times 4. You can instead solve this equation. Solve this. Okay. This can be solved using extended Euclidean, because 3 here is the GCD of A and B. So this can be solved using extended Euclidean. Then what you have values for x and y. For this one, it would be x is 2 and y is 5. Then you can multiply this equation by 4. Then you have 39 times 4 times 2 plus 15 times 4 times 5 is equal to 3 times 4. Now 4 times 2, 8 is the solution for x. And this is y. So x is going to be 8 and y is going to be 20. So understood? Did you understand? You need more clarification on that. And okay, now we can do the modular multiplicative inverse, but I will kind of skip that to skip into combinatorics, and I will share the Wikipedia page for modular multiplicative inverse. So, okay, so can I have a feedback, please? Is this understandable or not? Please, we don't have that much of time. If you did not understand, please let me know. Okay. So, okay, then let's move into combinatorics, our second main topic. And I needed to discuss some problems as well, but I'm not sure whether we will have enough time or not. But okay, let's see what combinatorics is. Now, first we have traditional counting problems. Counting problems. An example, a number of different words can be prepared, say prepared with the letters of some word. Let's say planet. Word planet. So you can use the counting principle here. So you have you have a word with 6 letters, and you are assigning. Now you can use these letters, and build different words. So what you're doing is you take the first position, and here we have 6 different letters to put into this position. Now we have put one letter to this position, and there is 5 possibilities because we can't use the same letter here. Therefore, we have only 5 letters in this position, and we have 4 here. 3, 2, 1. And we have to multiply these digits, and we will have a factorial of 6, which is 7 to 8. So this is a traditional counting problem. Okay, so this can be realized using taking the factorial. It is a pretty easy one. And there is a small complication for this one. If we have something like this, this word, what is the difference between these two words? Second word has same letters again and again. The repeating letters. There are repeating letters. We have 2 M's, 2 T's, and 2 E's. So, now see, now when we are doing this one, we are treating all the letters as distinct letters. But here, let's say we will take 2 possibilities. Let's say we have, don't have enough. Okay, let's say we have this word committee like this, and we exchange these 2 letters. It will not make any difference. We will have the same letter again. Okay, so for every combination like this, every permutation like this, we will have 2 copies because we have 2 M's. So the algorithm will try to make 2 different words by interchanging this one. And we need to make it correct. To make it correct, what we are doing is we have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 words here. So if we don't have repeated letters, this would be the answer. And we know that there are 2 possibilities with these words. It will try to interchange and make 2 words by these 2 words. So we divide it by 2. And for double T's, same thing happens. For E's, same thing happens. And this is actually the factorial, because if we had 3, the letter repeated for 3 times, we can have 6 different combinations. Right? Because if we have distinct letters, we can have 6 different permutations with this. So if we have same letter, the algorithm will try to make this 6 different permutations using the same letter, but it will not make any difference. Therefore, we need to actually divide it by. Can you explain without considering time? This session is more valuable. Okay, I am okay with that, but uh, is the organizing committee okay with that? Actually, I can explain it up to 9:30, or yeah, that's not a big deal for me. If the organizing committee uh, has some concerns, please let me know that. Because okay, so that is good. So if someone is concerned about time, actually you can leave. But I uh, is this I encourage you to stay here because we will uh, come into some interesting parts lately. Then we will talk about binomial coefficients. So this is a very interesting topic. Binomial coefficients. So what does this exactly give us is, say we have an array with 8 elements. So we have an array with n elements. Okay, and we need to take subsets which has k elements. We need to take subsets with k elements from this array. So the binomial coefficient gives us the number of different ways we can take subsets with k elements from this original set of n elements, right? So number of ways. It is fine to continue on with the session. Okay, organizing committee is okay with continuing the session without considering the time, but we will try to finish this session before 9:30. Okay. So this will give number of ways. Let's say we can choose an object as let's say subset of k elements from set of n elements. This is what this gives. This is a very basic thing, right? So the problem, let's see whether I will be able to think about the problem. Let's say, okay, we will take an array like this. Okay, so we will take out arrays with sub-arrays with 3 elements. So here n is 5 and k is 3, right? So we need to find the number of sub-arrays which has 3 elements each. How many possible ways we can do that? So before that, I will define the binomial coefficient. Binomial coefficient is something like this. We denote it like this. O, we say NCR, N choose R. It is something like this. N minus k factorial, N factorial. Okay. So this is, sorry, not N factorial, it's k factorial. This is k factorial. So now, say we need to take subsets of 3 subsets which has 3 elements from a set which has 5 elements. So n is 5, k, k is 3. So we can substitute 5 factorial, 5 minus 3 factorial here and 2 factorial here. So I will expand this to show you something. So 5 minus 3 is, so this is 3, okay. 5 minus 3 is 2. So we have 1 times 2 and we have 1 times 2 times 3. Okay. So now you can see we need to find the largest number here. 5 minus 3 or 3. 3 is the largest number. So we have more terms multiplied here. So we can actually cancel this one, all of these guys. Then we are left with only these two. Okay. In the downstairs, we have only this one. So to efficiently calculate the binomial coefficient, what we can do is, the answer for this one is 10. So we have 10 different ways to take three subsets with three elements from a superset of 5 elements. So what I want to say here is how to efficiently calculate this binomial coefficient. We can so I will stick with this notation because NCR notation is not familiar for me. So in K, so we have this one, n minus K divided by K. Okay, now for this one, we need to find the largest number from these two. What is the largest number from n minus K and K? So let's say K is larger than n minus K. This means K is actually larger than n by 2. That is obvious, right? If K is larger than n minus K, it means K is larger than n by 2. So now we can see that we have a higher number of multiples here, less number of multiples here. So we can actually cancel out all of these multiples with the multiples we have here from 1 to K, because K is always less than n. Otherwise, this is not defined. You will have an error. Okay. So we can actually cancel from 1 to K multiples from the upstairs. Then we have K plus 1, K plus 2, and all the way up to n in the upstairs. Downstairs, we will not have this one because this has already cancelled off. We have 1 times, 2 times, or the way up to n minus K. And if K is, this is true if K is greater than n by 2. If K is less than n by 2, what you do is you cancel off all the elements, all the terms from 1 to n minus K in the upstairs and start from n minus K plus 1 and go up to n. Then you divide from the product of integers from 1 to K. So that's it. That is how you calculate this binomial coefficient. So now there is something interesting with this binomial coefficients. Have you heard about Pascal's triangle? Is anyone familiar with Pascal's triangle? Yes, yeah. Pascal's triangle is something like this. We learned this during our ordinary levels. Yeah, thank you. Thank you for your feedbacks. And I will write another one. So what happens here is this digit here is the sum of these two digits. And this digit here is the sum of these two. That is how this is made. Now this will give, now say this element here, this is in the 5th row. So we start from 0, right? 0, 1, 2, 3, 4, 5. So this is the 5th row. So this will contain 6 values. These 6 values are 5, 0, 5, 1, 5, 2, and up to 5, 5. Okay. So that is the thing. And you know that the sum of these values is going to be 2 to the power 5 minus 1. Try that. No, 2 to the power 5. Exactly 2 to the power 5. 10 plus 10 is 20. 5 plus 5 is 10. It's 30, 31, and 32. So in this row, the sum would be 2 to the power 4, 16. Here it's 8, 4, 2, and 1. So that is the first pattern that you should understand in this Pascal's triangle. And you can see some interesting facts. See here. These are all 1, 2, 3, 4, and 5. Count it. Then you count from 1 to 5. and these are triangular numbers. You can prove that. And if you take this one, this as a number. This is 1. This is 11. This is 121. This is 1331. This is 14,641. Here, if you give this 2 to this guy here and give this one to here, you will have this one. So what are these numbers? What are these numbers? 111, 121, 1331, 14641, 161051. What are those? Can you guess? These are powers of 11, right? So these digits will give powers of 11. Actually, yeah, exactly. So you can actually prove this using linear algebra. I'm not going to do that right now. If someone wants the proof, this is a really interesting proof because we consider the fact that we can see the numbers as polynomials. There are lots of similarities going on. From linear algebra, we can prove that these numbers and polynomials fall into the same algebraic structure. So with that, we can say that this is something. So the properties of binomial coefficient, and using binomial theorem, we can prove that how this happens. Okay. So that is how it goes. So this contains the binomial coefficients, and there is an interesting recursive formula to calculate binomial coefficient, and it can be explained in a very interesting manner. The recursive formula is this. So how to explain this? The explanation is the most interesting part. So we have a set with n elements. Okay. And we need to take k elements out. So this associates with whether we are taking the ith element out or not. Let's say this is the ith element. And if we take the ith element out, then what we should do is we should take another k minus 1 elements from the other n minus 1 occurrences. If we take the ith one to this subset, then we need to choose k minus 1 from the rest of the elements in the original array. Then, if we do not take I, if we decide not to take I, then we need to take k elements from the rest of n minus 1 elements. So the actual number of combinations is the sum of these two. This corresponds to taking k elements from n minus 1, and this one the taking of k minus 1 elements from n minus 1 elements. So that is how this recursion works, and I have this recursion in my GitHub as well. So I really encourage you to clone that repository in your internal memory. It might not work as it is, but you can use them for problems. Okay. So that is how you, and another interesting thing, this these binomial coefficients are symmetric. You can see it here. If we divide this into two parts, these two parts are symmetric. Why is that? It is because, say you have an array with n elements and you are taking k elements out, it means that you are leaving k minus 1 elements. So eventually, you have actually found the number of possible ways to leave k minus 1 elements in the array. So that is similar to taking k minus 1, n minus k, not k minus 1, sorry, I will repeat. You are taking k elements out, and it means you are leaving n minus k elements in the original array. So by finding the number of different ways where you can take k elements out, you have coincidentally found the number of different ways you can leave n minus k elements in the original array. So it is similar to taking n minus k elements out from the array. So that is why these binomial coefficients are symmetric. Okay, then I hope that we can finish this by 9:15. But when I started this, I expected to finish this by 8:15. So do not believe me. So let's say this is okay. Let's talk about the differences between permutations and combinations. And combinations. Combinations. When we are finding the combinations, we actually do not consider the order. We just take three elements out, and here this is actually similar to this. So just this will take this as one choice. These two are taken as two choices. Here order matters. So when you are finding permutations, you take three elements out and you find the number of possible ways to rearrange those elements. You have an array with n elements. In combinations, you only take in an array with k elements. So that's it. But in permutations, you take an array with k elements and you rearrange the terms within that array. For an example, let's take this planet again. We need to find the number of, let's say, 3-letter words. So we have to take letters from this word planet. So let's say we have, now, if we use the binomial coefficient, what it gives is the number of different ways we can take three elements out. That's it. The order doesn't matter. It will take this P, L, and A out first. Let's say we got P, L, and A out. And once we get this out, we can rearrange these letters like this. A, P, L, and A, L, P. And we have 6 different possibilities here. And we can take another 3 letters. And we have another 6 different permutations there. Okay. So what we are doing here is we are taking the binomial coefficient, then we multiply it by the factorial of k, because if we take k elements out, it will have k factorial permutations. We have talked about that since we do not have repeated letters here. If we have repeated letters, we have to deal these as two cases where we take an subarray which has distinct elements and where we take array which has repeated elements. We have to treat as two different cases. So what we are doing is we are taking k number of elements out and we are rearranging the elements of that subset in different order. So there are k different ways to do that. So if we substitute this, we have this times k factorial. So we can cancel this out. We have this minus k. We denote this as NPK. P is for permutations. For combinations, we said that it is NCK. And for combinations. So NPK is n factorial divided by n minus k factorial. Now, I have not talked about modular multiplicative inverse, but you know about multiplicative inverses, right? Multiplicative inverses is something that you have a number called 5. The multiplicative inverse would be 1 over 5. It means 5 times 1 over 5 is 1. This is 1. So we need to find a number. When it is multiplied by 5, it should give 1. So that is the multiplicative inverse of 1. So in modular arithmetic, we denote it as this. This is an additional note. Okay, you should go and search how to find this in programming. So what you need to do is you just solve a linear differential equation like this. My equals 1. This is the linear differential equation you need to solve. So if you solve this, the x would be the modular multiplicative inverse. So you need to prove that this gives the modular multiplicative inverse. And when talking about modular multiplicative inverses, we need to know that A and M should be co-primes. What are co-primes? Co-primes are nothing but the GCD of A and M should be 1. So this means A and M are co-primes. It means A and M does not have common factors, right? Something like 26 and 15. GCD is 1. So this 26 has factors 2, 13, 1 and 26. 15 has 1, 3, 5 and 15. But these two digits does not have common factors rather than 1. So the greatest common divisor would be 1. So we call that kind of integers are co-primes. So actually this modular multiplicative inverse exists only A and M are co-primes. If A and M are not co-primes, there will not be modular multiplicative inverse. So we need to make sure that A and M are co-primes. Otherwise, modular multiplicative inverse does not exist. Now in programming comparisons, now I'm going to give you a tip where how you can optimize finding binomial coefficients mod M. Now in programming comparisons, you have seen this 10 to the power 9 plus 7. You have, so if you have big numbers as solutions, they ask you to take the modulo with this guy. So what is the special? Now this is an additional question. What is the specialty of this guy? What is 10 to the power 9 plus 7? Why they give us 10 to the power 9 plus 7? Why don't they give us 10 to the power 9 plus 8? Or 10 to the power 9 plus 4? Why they always give this one? Why is that? Any answer? Any guess? Okay, I'll give you 5 seconds. It's just give me a, yeah, exactly. This is a prime. This is the first prime after 1 billion. This is the first prime after 1 billion. That is why they are giving this to you because of this case. Okay. The modular multiplicative should exist. Or in other words, if these two are co-primes, for every value from minus infinity to plus infinity, or for every value from in the range of M, there would be unique map when we take mod M. So we can actually reverse it and extract the original number. Otherwise, these answers would not be unique. In other words, another problem with that, if A and M are not co-primes, the modular multiplicative inverse will not define. Therefore, we can't take a risk. If we give a composite here, there can be some numbers where the numbers which have common factors with this guy. But if we give a prime is a co-prime with any other number. Prime is a co-prime with any other number. You need to check on Euler's torsion function and all, and you know that Euler's torsion function for a prime is prime minus 1. If you don't know, you search for Euler's torsion function. It has something to do with co-primes, right? So the prime is co-prime with every number. Therefore, if they give us a prime to take the modular multiplicative inverse, they can make sure that always the modular multiplicative inverse exists. Now, say you need to find NK. Let's say you have to find it, the modulo of 10 to the power 9 plus 7, let's say mod M. M is 10 to the power 9 plus 7. So let's say for this case, k is greater than n by 2. And we have derived that this can be k plus 1, k plus 2 up to n divided by 1, 2 up to n minus k. This is the simplified version. And you need to take mod m. Now, they are asking us to take the modulo m because this number is going to be huge. So it is so much inefficient to keep large numbers. Okay, so as a solution, what you can do is, now we have discussed some properties of module, and we said that AB mod m is A mod m times B mod m. And what we can, so what this means is we can distribute the multiplication under the modulo from m. So we can do the same thing here. We can, instead of simplifying this whole expression and taking the modulo, we can actually take 1, and now what we are doing is we are running a loop, right? We are running a loop. We start from k plus 1 and go up to n. So we can keep two variables, numerator and denominator, and initialize with 1. And you need to go from k plus 1 to n minus k, and you need to multiply numerator by this in the first iteration and the denominator by 1 in the first iteration. So once you multiply this by k plus 1, what you should do is you take modulo of m at that stage, because we can distribute this multiplication with this modulo. So it is similar if you multiply all the terms and take the modulo, or if you take the modulo and multiply. And you can do the same for numerator and denominator. And then what should we do for the division? It's pretty easy. What we can do is we can take the modulo multiplicative inverse of the denominator and multiply by the numerator. That is how you can optimize this. So instead of taking this big guy and take the modulo, what you should do is you should take the modulo after each step for denominator and numerator. So you have numerator modulo m and denominator modulo m separately. Then you find the modulo multiplicative inverse of the denominator and multiply that answer by the modded numerator. Then you take the mod of the whole thing. Then you can calculate the binomial coefficient modulo m very efficiently, because we know that instead of dividing by 5, we can actually multiply by 1 over 5. So if something has a multiplicative inverse, instead of dividing by that thing, we can actually multiply by multiplicative inverse, right? So we can use the same trick here. So it will optimize the code. So that is a trick that I use. Then I will talk about Catalan numbers, and then we will talk about principle of inclusion and exclusion, and that would be the end of the session. So Catalan numbers. Catalan numbers. Here I will teach this in a very simple manner. Now here you have two operations. Let's say A and B. Two operations. You can do both of these operations, and you are allowed to do one operation for n time. You should do A for n times and B for n times. You can't exceed the limit. You can't do n plus 1 operations, and you can't do n minus 1 operations at the end of the day. When you are done with the problem, you should have done both operations for n times. Okay, at the end, you should have done all the operations for n times. But there is another catch. Catch is, let's say for a certain time, for a given time, Now say you are doing this operation. Let's say you have done A, then you do the operation B, then B, then you do A again, and you go like that. So at a given time, you find now at this time you have done only these things. This is not done yet. So at this time, the number of times that you have done the operation B should be less than or equal to the number of times you have done the operation A. It means you can't do operation B 3 times before doing operation A for 3 times or more. So it means you can't have something like this because you have done A for 1 time but B for 2 times. This is wrong. If you need to do B for 2 times, you need to do A for at least 2 times. It is okay to do A for 3 times and do B for 1 time, as for 2 times. That is really okay. But always during the process, the number of occurrences of A should be greater than or equal to the number of occurrences of B. That is a condition. And when you are done with this process, let's say A and B, this should end with B. Otherwise, the condition is violated. You should have n A's and n B's. This is a must. You can't have n minus 1A. So they are allowing you to do B operation for n times, and you should use all the resources. You have to do it for n times. So something like that. So the very common problem comes with this uh, these conditions is to build the valid bracket sequences. Valid bracket sequences are like, now say you have open brackets and close brackets. So if you now you can start a bracket and you can close a bracket. These are 2 operations that you can do. For a valid bracket sequence, before closing a bracket, you should open it. So you can't start from this. Okay. So now say you have 2 brackets like this, you have opened 2 brackets, and then you have closed one, then you have opened one, then you have closed two. Now this is a valid bracket sequence. See, because these 2 brackets are open and this bracket is closed, and you open this bracket, then close that one, then close this one. This is valid. But if you open one bracket, close it, and you close again, this is not valid because you did not open this, but you have closed it. You can do something like this. This is okay. Then open this or close this. This is okay. This is a valid bracket sequence, but this is not a valid bracket sequence. This is wrong because you have closed this bracket and closed another one before opening that. So you can't close a bracket before opening a bracket. So this can be realized using Catalan numbers. So Catalan numbers is, let's say, Cn given n. You can 0, 1, 2, 3, 4, and there might be some numbers for Catalan numbers. So now say you have n brackets here, and you need to calculate the number of valid bracket sequences. So that would be Cn, the n Catalan number. Okay. So how can we find this Catalan number? That is, we use an interesting trick. What we do is we divide this in a certain place, and we find the number of valid bracket sequences in this side and this side. We are trying something like that. With that, we can find a recursive formula, but without that, we can actually take an approach like this. Now say we take an invalid bracket sequence. This is invalid, right? So what we do is we start from here. Still it is valid. Here valid. Here are not valid. We take this one. The first occurrence where we, when we move from left to right, the first occurrence where we find an invalid bracket sequence, we stop there and we reverse these brackets. These 3 brackets, we reverse. Then we will have something like this. So here, why this is invalid is always there would be, if we have k open brackets, we will have k plus 1 close brackets in a situation like that. Okay. So if we flip that, we will have 2 open brackets and 1 close bracket. So altogether, we will have in the entire subset, in the entire bracket sequence, we will have n plus 1 open brackets and n minus 1 close brackets. So this is for an invalid bracket sequence. Now, when we are given with n brackets, regardless of checking the validity, how many bracket sequence we can make all together? We actually given 2 n brackets. This is like a word, and we need to find different words, but we have the same letter. Opening bracket is a letter, and the closing bracket is also a letter. So we have n open bracket. So we have n repeated letter and n close bracket. Another n repeated letters. So this is similar to 2n choose n. See, 2n divided by 2n minus n factorial times n factorial. So this is the total number of bracket sequence. So to find the valid bracket sequence, what we need to do is we need to, so that would be the nth Catalan number, we can take all the possibilities and subtract the invalid ones. So invalid ones, what is the condition? Instead of taking n open brackets and n close brackets, we will take n plus 1 open brackets and n minus 1 close brackets. So it would be 2n n plus 1. Okay, so this is, with this we can calculate the Catalan number and we can actually simplify this. 2n choose n, 2n choose n plus 1. Okay, so we can like this. So 2n choose n plus 1, we can say that this is n, so this is minus n over n plus 1, 2n n. Is this clear? Because 2n, 2n n plus 1 is 2n factorial divided by n plus 1 factorial, n minus 1 factorial. So to make this 2n divided by n factorial, here we have products from 1 to n plus 1. So we need to multiply this by n plus 1. Oh, I think I have. What is the error here? Okay, so you know, n plus 1, n minus 1. Oh, no, sorry, the other way around, right? So we need to actually use 2n and n and build 2n n plus 1. We can build this one using this. Okay, so what we should do to have n plus 1 factorial in the downstairs, we should multiply from n plus 1. And to have n minus 1, we should divide by n. Means have something like this. So if we simplify this, we will have something like 1 over n plus 1 to n n. So this is the nth Catalan number. So if you have a problem where you should have conditions like this, you have two operations and you should do both operations for same number of times, and this condition is there. You can't do the second operation for k times before you do the first operation for more than k, for something more than k, not strictly more than k times. So if you have something like that, you can use this. Now, there was a question that I have made for pre-recorders. It means it has some guy with a jetpack, and he tries to come from this point to this point, but he can only go for two directions for one unit. He can either go straight for 1 unit or go down for 1 unit. Now this satisfies this condition. See, at the end of the day, he should come here. So this would be n units behind this. It would be n. This would be n. So you have to do the forward function for n times and downward function for n times. And if you have done the forward function one time, you can't do the downward function for 2 times. So you will end up below the flow. That is not valid. So here you can do it 2 times and you will reach the flow. Like that, you can't do the downward function until you do the forward function. So this will result in a Catalan map. So that is how you find Catalan numbers. And I will do the principle of inclusion and exclusion and show you a problem, and then I will stop this session. Inclusion and exclusion. So here what we are doing is, now say we have done this in our advanced levels. Now say we have two sets like this. Let's say this is A and this is B. Okay. So this is the intersection of A and B. So what we need to find is the size of the union of A and B. A union B is all the elements in both A and B, but element should not repeat. So we can actually do this by adding A plus B, A and B, the size of A and size of B. But you can see here, this area is added twice. When we add A, it will add all of these elements. When we add B, it will add all of these elements. And this is added twice. Therefore, we should subtract it for one time. Okay. So this is how it works for two subsets. So if you have three, say 3, it will look like this. It's so hard to draw. Let's try. No, it is not hard to draw. Now you start by adding A's, adding the sets with single sets, and with that you add these things. I will color them. These things twice. Therefore, you have to subtract all of these things. It means A, B, A, C, B, C. And then, now see this middle part. What happens to that? When you add these 3, it will be added thrice. And when you removing these things, it will be removed for 3 times. So now it is not here because you have added it 3 times and removed it 3 times. So you have to add it. So this is valid for any case. Now say you see here you have only one element, one array. So you are adding that. Here you have 3. You are adding that. Here you have 2 and you are subtracting that. So when you have even number of sets, you always subtract. And when you have odd number, you are always adding them. That is the principle of inclusion and exclusion. So now say you need to find the union of A, B, C, and D, then there would be more than one cases with 3 sets. You have to add them all, and there will be one case with the intersection of A, B, C, and D. You have to subtract that because that is an even case. Okay, so that is the principle of inclusion and exclusion. So the problem that I needed to show you is when you see this problem, okay, this one. When you see this, you will not see that, not see this as a combinatorics problem. What this says is you are given k distinct prime numbers A1, A2 to AK, an integer n. Your task is to calculate how many first in positive integers are divisible by at least one of the given prime numbers. Okay, so let's take the example here and discuss that. So we have 20 as in primes 2 and 5. So what you should do is you should find how many integers are from 1 to 20 which is at least divisible by 2 and 5. So you have integers from 1 to 20. So this is sample space. In the sample space, you have all the digits from 1 to 20. And you have to check whether you have to start from 1 and check whether uh, does it does the integer that we are considering is divisible by 2 or 5, at least from 1. It is okay to divisible by both of these. So we can have two sets. This is divisible by 2, let's say D2. This is divisible by 5, let's say D5. Okay, so you can find the number of integers in the range of 1 to 20, which is divisible by 2, by dividing 20 by 2. And you can do the same thing for 5. So I will do that here. So this set, you can find the value of this set by dividing 20 by 2. This one dividing 20 by 5. So there would be 10 integers from 1 to 20. The inclusive interval, there would be 10 integers. Yeah, 2, 4, 6, 8, 10, up to 20, there are 10 integers. Divisible by 5, there are 4 integers, 5, 10, 15, and 20. So now we can, if we find the number of distinct integers, which is divisible by either 2 or 5, like this, let's say the answer. If we add these two, what happens? How about a number like 10 and 20? How about 10 and 20? It is added twice because here we have 10 and 20. Here also we have 10 and 20. It is because those two are in this intersection. Therefore, we have to, by the principle of inclusion and exclusion, we should find the intersection. How? We should divide 20 by the LCM of 2 and 5. That is 10. Because the LCM of 2 and 5 will be repeated. This is 2. You should subtract 2. So you will have 12. So here you can see 12 is here. So this can be solved using the principle of inclusion and exclusion. Okay, so guys, that's it from my side. So do you have any questions? So please make it quick because we have already run out of time. So are there any questions?
Yes, so if you have any questions, you can either unmute your mic and ask directly, or you can drop a message in the chat box so I can read out the question for Athulya.
You're welcome. If you have any doubts with the theories that we have discussed, you can always reach me out. Anuka can, if you have contacts with these participants, you can share my email or some contact, some way to contact me. I'll send you my email. So for now, if you have any question regarding anything we have discussed today or regarding anything about comparative programming, especially discrete mathematics, anything means I will try to do give my best answer.
Seems there are no questions. So is it okay if we wind up the session now?